Okay, welcome to this week's Origins Colloquium. It's great to have Brett back at Charlottesville to give a talk this week. So Brett received his PhD from Caltech in 2014. He was then I think the Jansky first, then Hubble. Is that right?
Yep.
So based in Charlottesville and Harvard, and then in 2020 started a faculty position at MIT, where he's now associate professor in the chemistry department. Brett has worked on a wide range of topics in astrochemistry, both lab side and observational side. I think we'll hear some of those aspects today related to the origin of PAHs. So welcome, Brett.
Okay, thanks. So Jonathan asked me to give this talk, I don't know, what, a month and a half ago or something when we saw each other in Greece. And I agreed on the condition that I could just use the last half-hour talk that I had given. We're going to talk a little bit about work on figuring out the chemical origins of PAHs in the specific source TMC-1 that my GOTHAM collaboration looks at. And I'll just give you a preview of what the talk is going to look like. Look, it works. It's going to look like that, right? So basically, we don't understand the chemical origins of PAHs, and we have a whole bunch of random ideas that we're going to smash together. I'm going to throw them all at you and say that we think there might sort of kind of be a coherent picture here emerging in a few years. So that's where we're going to work with. So PAHs, polycyclic aromatic hydrocarbons. I'll give a brief overview for those that aren't embedded in this. So PAHs have been known to be around, or at least strongly suspected to be around in the interstellar medium dating back to the first observations were in the 1970s. But they were assigned as carriers of these unidentified infrared bands or aromatic infrared bands in the mid-1980s. These strong, bright, distinct emission features in the infrared are characteristic of the stretching and bending motions of carbon and hydrogen atoms with respect to one another in large polycyclic aromatic molecules. Now, you'll notice that all that's been labeled here are the motions, right? Not individual species. I've shown chlorine over here because it's one of my more favorite molecules. But you can't actually look at these infrared bands and say which PAH those signatures are coming from. Now, in the laboratory, you can take a bunch of different PAHs and a high-resolution FTIR instrument, and they'll all have unique spectra. It's quantization, right? Quantization of energy levels, vibrational energy levels of molecules are distinct. They are unique. However, the CH stretch and the CC stretch and the CH bend of one aromatic molecule looks an awful lot like that of every other one. They're unique, but they're very, very similar. And so in space, where we likely have dozens, if not hundreds, probably thousands of different types of these, all emitting at us along these vibrational frequencies, they all just sum up to this aggregate spectrum where we can't pick apart which individual ones they come from. We can say, yes, it's very clearly the pattern associated with this particular motion in this class of molecules. Can't tell you which ones in particular. Now, that said, we have a good idea about the excitation mechanism behind this. Basically, these molecules are illuminated by ultraviolet radiations, typically show up in UV enhanced regions like PDRs or centers of galaxies, that sort of stuff. And then they relax by cascading through fluorescent emission through these vibrational energy levels. And because we have an idea of the excitation and relaxation mechanism, and because we have an idea about what modes are happening there, we can then look at the intensities here, look at how widespread they are, and back out how much of these must be in space. So if you make all of those assumptions, then something like 10 to 25% of all carbon in the universe is in a PAH, which is a kind of a wild number. 25% is the very upper end of that range. I don't believe that. Some of the numbers go down all the way as low as a couple percent. That's probably also not right. So pick your favorite number in between there. That's probably the about right target, 8 to 12% or something. Right? But we don't know which ones they are, which is kind of embarrassing. So we've been working on this as a field for 40 years, and we can't figure out which individual ones are out there, meaning we don't understand where maybe up to 25% of all of the reactive organic carbon in the universe is actually hanging out in terms of wanting to do chemistry. Now, I do like a little bit of history of science. So I want to show you, you may have seen this before, but one of the earliest experiments that was done in the laboratory to try to assign these features to PAHs They had some low resolution interstellar spectra, and they thought, well, this might be PAHs. How do you get a mixture of PAHs on Earth? You swab the tailpipe of a car that has been poorly tuned. Because PAHs on Earth are the products of incomplete fossil fuel combustion, right? They're also like if you burn a birthday candle and you get black soot on the ceiling, that's all PAHs, right? So here's the comparison. They swabbed the tailpipe of some car, right? Made sure it was a poorly tuned engine, and it matches up really well, right? You even get the little shoulder bump right there versus the Orion bar. This is a PDR emission there. So I just think that's really cool. That's back from Lou Alamandola's paper in 1985. All right. So where are PAHs in the universe? Well, they are everywhere. So they have been very recently found, at least the single ring building block of benzonitrile here in shock cold clouds in the galactic center. So this is a cold dark molecular cloud that's been hit by some sort of relatively low velocity shock and pushed all of the molecules that were in its ice mantle up into the gas phase for detections. This was work by Victor Revilla using the his 40-meter telescope just earlier this year or late last year. They're in protoplanetary nebulae. So actually the first detection of benzene, that single ring, was in this protoplanetary nebula CRL 618. It's very carbon-rich sources. They're being found in disks. So here's a detection. We have detections of PAHs themselves in disks. So I think this one's really, really cool. This is the detection of benzene, that single ring here, using the JWST in this disk around a very low mass star. They're also found in diffuse clouds. So there are specific sight lines toward very bright background absorbing stars in our galaxy that go through diffuse material. And you can actually see the absorption spectra in this case of PAHs. So they are floating out at the earliest stages of star and planet formation. As I said, they're found in PDRs. So the PDRs for All collaboration was this early release science program from JWST that decided to do spectroscopy and imaging toward PDRs and galaxy, and they'll do these slices through the PDR front. So here's material that is being obliterated by these nearby UV bright stars. There's absolutely tons of PAHs there. And again, they're even being seen actual PAHs, as I mentioned, in disks. So here's another paper on JWST spectra of PAHs themselves in emission in protoplanetary disks. Protoplanetary disks, we don't think about it, but they're also mini PDRs, right? They're very young stars. They put out a lot of UV radiation. That UV radiation impacts onto the surrounding material. That's not as widespread as the Orion bar or the Horsehead Nebula, but it is still a PDR nonetheless. Now, where we have focused, and the Gotham team, which was started here at NRAO when I was still a postdoc, is on a cold, dark molecular cloud. That's TMC-1. So this is actually the torus molecular cloud imaged from my apartment complex here in Charlottesville, like 10 years ago, which I think is really cool. And most of the work that's been done on this source in the last, say, 10 years has been the product of two different collaborations and surveys. The first is the one that I'm involved in, the Gotham collaboration. It's GBT observations of TMC-1 hunting aromatic molecules, which I think is a good acronym as far as astronomy ones go. So this is done with the Green Bank telescope just across the way. We cover the low frequency end to pretty high sensitivity. We think it's pretty high sensitivity with extremely high spectral resolution, and that'll come into play in a little bit here. The most recent overview paper here is by Ceci Zhu. She's now a cosmic AI postdoc up at NRAO. So if you haven't met her yet, go meet her. She's awesome. And if you want our data, it's all publicly available in this paper. So you can go download it. It's fully reduced, ready to use and analyze form. The other survey is the Quixote survey, which I cannot remember what the acronym stands for, and they don't have a really cool logo. So there's a picture of their telescope. They have this 40-meter telescope in Spain. So this one started off in the Q band, 35 to 50 gigahertz here. And they've achieved exceedingly high sensitivity, way higher than we have, despite being a much smaller telescope. And the way that they did that is that they built this brand new state-of-the-art, nothing like it instrument, receiver, and spectrometer that covers this entire range in one shot. Right? So at GBT, to get this amount of resolution, we get about 1 gigahertz of bandwidth if we're lucky. Here, they get 15 gigahertz of bandwidth all in one go. Now, to do that, they've sacrificed some on the resolution here, right? So it's substantially worse resolution than ours, but it's still very high resolution by astronomical standards, which is really great. So that means that, we spent 1,500 hours integrating over this observation range across like 37 spectral settings. They've spent 1,500 hours integrating on this range in one spectral setting. All right, so the hours just add up better. They also now have expanded this down into the K-band region, 18 to 26, and they have some preliminary results out of that. Well, I haven't seen a lot more out of that recently. So a lot of the larger molecules, because we go to lower frequencies, end up in ours, and a lot of the medium and small size molecules end up in theirs. So this is where we have been looking for PAHs, and we have come up with a remarkable number, right? Because we're working with radio astronomy, we're working with rotational spectroscopy, not vibrational spectroscopy. The rotational spectra of PAHs are fully separable, completely unique. Vibrational spectra of PAHs are unique too, but they're very similar. The rotational spectra of these PAHs are completely different from one another, right? So in our source, TMC-1, which has extremely narrow lines, we can identify all of these individually with great confidence, and we don't have to say that this is the aggregate emission spectrum. So we've been able to start piecing together exactly what PAHs are present in this source. So it started with these 2-ring species, cyanonaphthalene in 2021, all the way up to this 7-ring cyanocoronine in 2025. You'll notice most of these have a CN group attached to them. The failing of radio astronomy and rotational spectroscopy is if the molecule doesn't have a permanent dipole moment, you can't detect it. It doesn't have a rotational spectrum. Turns out that PAHs will react readily with CN radical if it's anywhere nearby. There's tons of CN radical in space, and so we just look for the CN derivative instead. We take a hit in abundance. It's not a 1-to-1 reaction rate, right? But the dipole moment becomes so large that we can usually still detect this derivative. So the ones in blue here are all the ones that were detected by the Gotham team here. This one was detected by both of us. This was work led by Andrew Burkhart, who was a grad student here. And then the CN version of Indene here was led by Maddie Sita, who's an undergraduate student here at UVA. And Brian Chingala, who was at the CFA and is now at Boulder. And then all of these large ones up here were led by research scientists in my group, Krabby Wenzel, and assistant professor at UBC, Elsa Cook, who is also a graduate of UVA. So she got her PhD in chemistry, in the chemistry department, before working in Rennes for a postdoc. This is really cool. So what have we learned about this? Well, one of the cool things that we learned about this is that there's an awful lot of these molecules in this source, not just in the variety, but in absolute abundances. You can do some back of the envelope calculations. And again, like the abundance estimate for the ISM, very back of the envelope. But depending on the assumptions you make, something like 0.1 to 0.5% of all carbon atoms that are not in CO are in a pyrene molecule in this source, which doesn't sound like a lot, but think of the hundreds of different molecules that are there. We know there's hundreds of molecules there. We've detected them. And there's probably 4 times as many at a relatively comparable abundance that we haven't detected yet, just because I don't have the lab data for it yet. And 0.5% of all of that carbon is in a pyrene, if you don't count CO, which isn't a real molecule anyways, right? So it's a huge abundance of this species, right? Which was unexpected to us. So we want to think about how these molecules are formed, right? So there's a couple of different historical ways that we think about these molecules, PAHs being formed. They have names. I'm going to tell you the names for the routes. The names are stupid, but I didn't come up with them. So the first route is called the top-down route. And the way the top-down route works is that you start building PAHs from the bottom up until they get very large. And then they exit the region where they're being made, and then they get broken back down from the top into the distribution that we see wherever we're looking, right? So build them up in one place, stop building them, they get broken back down into what we see. And there's a bunch of different ways to make this route work. Primarily, we think this happens in the immediate surroundings of post-AGB stars, evolved stars, carbon stars. And the reason for that is that there is a huge amount of energy and material and high densities available in this environment. Basically, it looks like a flame here on Earth, which is where PAHs are made on Earth. They're made through combustion. And so you can go through reactions that look something like this. It's called a hydrogen abstraction acetylene addition. That's hiding behind this notification here. So the Haka route. There's a bunch of other reaction mechanisms that look similar, but they all sort of work like this. You assume that you start with a benzene ring. Choose your own adventure for how you make that. But then you bring in acetylene. This is just a 2-carbon unit here, and you pop off a hydrogen and form a bond to it. Then you bring in another acetylene, pop off 2 more hydrogens, form 2 more bonds, and now you have a ring. And you can keep doing this as many times as you want. And because you're only bringing in 2 carbons at a time, you can build those rings in any decoration pattern that you want, right? You could add 4 in a row here. You could close this loop here. You could add some dangling off there. You can make basically any PAH using this top-down hot chemistry like this. The trick is, though, you really do need that heat. Every single one of these steps has an activation barrier, which means that if you exit the formation region around these stars where you have energy, all of these routes turn off. They don't work anymore. So the other way to make this is what we call the bottom-up route. They're both bottom-up routes, but fine, this is the actual bottom-up route, which you start in cold sources and you build them up directly into the distribution that we see. So instead of building them very large and breaking them down, you just build them up to what we see today from the starting materials. And this is supposedly able to happen in cold environments. Now, in cold environments, those Haka-type routes don't work. There's no energy to overcome those activation barriers. So there's a more limited set of mechanisms that work. Most of them look something like this, the hydrogen abstraction vinyl acetylene addition. Again, you assume, choose your own adventure how you make it, a benzene ring exists, and then now we're going to add all 4 carbons at once. Right? If you start with all 4 carbons, the reaction energetics here means that there's no activation barrier. It's great. So you just form those 2 bonds, you pop off those hydrogen, form those bonds, and now you've made a ring. But you can imagine now this is less flexible. If you're bringing in all 4 carbons at once, you can't very easily add in rings along this bay, right? Because then you'd have 1, 2, 3 carbons plus 4 more. That would be a 7-membered ring instead of a 6-membered, right? So because you're working with a bulkier unit, you have less variety in what you can make. And in fact, this is pretty universally true from what we've found. There are far fewer routes that work from the bottom up at low temperatures, and they make a much more limited selection of PAHs. Now, folks in the laboratory like Ralph Kaiser in Hawaii are constantly finding new routes, right? We just don't know of as many as that Haka route. It's just less flexible. So the other thing that we didn't talk about here is the potential inheritance from one to the other, because this top-down route, we could make them from bottom up, make them very big, and then have them exit this region and start getting broken down. And those could just float to our dark cloud, to TMC-1, and get incorporated there, right? And that's absolutely true. There's one caveat, and that's that they're exposed to the background UV radiation of the galaxy, right? And so what we think happens, based on some experiments and some calculations, is that the small ones get obliterated. Anything less than 20 or 30 carbon atoms get obliterated before they could make it to that dark cloud to get incorporated. Now, that was the understanding as of maybe 3 or 4 years ago. There's actually some new evidence in the lab, mostly from the group of this team led by Mark Stockett here, that shows that there's actually, for some of these molecules, like cyanonaphthalene and indene and indonyl cation here, that have some fluorescent processes that allow them to absorb that radiation and then shed it back out as light before they blow themselves up. So there's some increasing evidence that maybe there can be some survival of these small molecules. Now, we can also get some evidence from our own solar system about whether the top-down or the bottom-up route is actually what's happening. So the Japanese Space Agency sent this really cool mission out to an asteroid in our solar system, Ryugu, back in 2014. It landed samples back on the Earth, which means we can use much more sensitive instruments here to actually see what's in there. And they found PAHs, which is really cool. But the instruments are sensitive enough, you can do isotopic analyses. And isotopes, the isotopic enrichment of the sample, depends on the temperature at which that sample was formed. So they can actually back out what they think the formation temperature of these different PAHs was. And there's very clear signal. These 3-ring PAHs had isotopic signatures indicating formation at more than 1,000 Kelvin, so top down, right? Evolved stars. And these, naphthalene, fluoranthene, and pyrene, by the way, we found naphthalene and pyrene at 10 Kelvin in a cold dark cloud, have signatures consistent with formation at 10 Kelvin, cold dark cloud, which is pretty cool. That also means that, well, both routes seem to be contributing. Is interesting. So I have to figure out what the actual balance of those is. So how do we work out what we think the chemistry is from the bottom up? Because that's what we're interested in. That's what we're seeing. Well, we can use astrochemical models, right? These big modeling networks like Eric Herbst and Rob Garrett use. So we did that. This is what we came up with. These were our modeled abundances, and those were the measured abundances. That's 6 orders of magnitude that we are off by. right? We could not reproduce these either for benzonitrile or for cyanonaphthalene. Those are the original ones. We put in a ton of work. These are the modeling team here. They put in a ton of work to try to improve those models, and they did. They made order of magnitude or 50 times improvement, but we're still dramatically undershooting those, right? And so that was a bit of a bummer there. We kept thinking about this for a while, kept adding more reactions to the network. Eventually, my graduate student, now postdoc Alex Byrne here, focused on the propargyl radical. This is a 3-carbon species, and managed to get some additional improvement, about another half of an order of magnitude here, in agreement between the observations for propargyl radical, this key precursor to PAHs, and what was in the model, but still couldn't actually reach that. So propargyl radical, this C3 species we think forms benzene, still dramatically underproduced. We come out that basically all of our PAH chemistry downstream depends on C3, though. So maybe even just making this small little update helped us with those cyanonaphthalene abundances. We're not the only ones that have been working on this, though. Just earlier this year, maybe 2 or 3 months ago now, Loison et al., working with Valentin Wakeland's group here, put out an updated model on the formation of benzene and its derivatives, focusing on that C3 chemistry that we said was so important to the formation of benzene. And they found that, well, this reaction here between C3H3 plus and C3H4 very rapidly forms benzene precursors here. That's the majority of the things. And these reactions were not in the network. And as soon as they add those, here's our measured abundances, this gray band here. Here is their predicted abundances from the model. The gray vertical band is the age of TMC-1. You can see pretty much exact agreement between our observation and what was in the model, which is really cool, right? That means that we're starting to be able to piece together that first ring, at least. And Alex actually tells me that incorporating some of this into our model dramatically increases the naphthalene abundance as well. So it's having the appropriate downstream effect on the formation of PAHs. Now, we've been working all of this. I mentioned a name earlier, a guy from the lab, Ralph Kaiser. He's an experimentalist. He measures a lot of these reactions to students, measure a lot of these reactions in the laboratory to try to figure out what the products are, what the branching ratios are, which ones will go under cold conditions and which won't. And in a lot of his papers, he also has a modeling colleague here, who consistently claims that they can reproduce all of our observed PAHs all the way up to cyanonaphthalene perfectly using their models, which is cool. But they don't provide their models or any of the reactions that go into those models, other than the reactions they're specifying in the paper. And we couldn't actually figure out what was going on, because even when we put in the new reactions they said that they were working with, we couldn't get, and we were off by orders of magnitude. Right? So we spent quite some time actually trying to dig into these. And it turns out in their supplementary information here, it says to derive the quantitative results, first, a time-dependent gas phase model was run until the system evolves to steady state. So they just let the dark cloud model go. That did not make enough benzene or PAHs, nothing at all matching our observations. But then they injected all of the ice mantle species into the gas phase. So at some point they said the cloud has reached steady state, and now I'm just going to take everything that's in the solid and put it in the gas. And then they let it run again. And when they let it run again with that new injection of species, this is when you get this match, right? And we found this very strange. How can you just decide I'm going to take everything from the grain mantle and put it into the gas phase, right? Well, the only way to do that in cold conditions is to use a shock. And TMC-1 is kind of considered to be a quiescent region. There's nothing going on here. It's the perfect cold dark cloud. But one of the Gotham team members, Steve Charnley, said, well, now hold on a second. I thought about this a long time ago. Said, look, back in 1990, I went through and I thought, what would happen if hydromagnetic waves propagated through cold, dark clouds and caused chemical fractionation? Could shocks be a major contributor to the observed dark cloud chemistry? And the answer was yes, this would substantially change things, which makes sense, right? So how do you actually make those? Because there's nothing in here, it's not supernova or something nearby. It's not a protostar. How do you put shocks into TMC-1? Well, a few years later, 17 years later, is this paper that said, well, look, cloud-cloud collisions could actually generate these shocks, right? So if your cold dark cloud just happened at relatively low velocity, to just run into another cloud, this could actually drive shocks of appropriate intensity through to actually drive some of this chemistry. You see that authors are same here. So, well, what else do we know? Well, Andrew here, again, back with Eric when he was, I started this as a graduate student and finished it as a postdoc, looked at how those shocks can affect the actual chemistry. And even low velocity shocks, you can briefly reach temperatures of more than 1,000 Kelvin, which can unlock high temperature hydrocarbon chemistry if you can actually inject anything into the gas phase. So is there any evidence whatsoever that a shock went through TMC-1? Well, TMC-1 is interesting. There's actually, it's not this sort of homogeneous single monolithic cloud structure, right? Going all the way back now again to 1997, it looks like there's actually clumps within this region here at different velocities. So this is all the same region, just set at different VLSRs, and you can see that the density structure in TMC-1 is changing. And there were actually some observations here, relatively high resolution for the time, that said, yes, if we look at CCS, we can see multiple velocity components pointed to this singular, supposedly monolithic, homogeneous dark cloud. And actually, with more modern observations, very high resolution using Nobayama, you can see there's 4 distinct velocity components. Now, the line width of this total thing is like less than 1 kilometer per second wide. This is still an exceedingly narrow line. The line width of these individual components is exceedingly narrow. These are very closely spaced in velocity space, but they are distinct and they are measurable. And in fact, with the high resolution of the Gotham observations, all of our molecules, we can fit those individual components. This is from the cyanopolyines paper that Ryan Loomis at NRAO worked up here. You can't actually see the data behind there because the green line is such a good fit, the observations, right? But we're still seeing all 4 of those velocity components. And we actually think there's chemical variation between them too. It's cool. We even have, after some heroic efforts by Ceci and Emmanuel Monge and others, some velocity resolved VLA maps of the source that we're working on now too. So there are 4 different velocity components. That means there's 4 unique clouds there. And their spatial distribution looks like they may have passed through one another in something of the recent history. And that means that there could actually have been a cloud-cloud collision that drove shocks that put some of this material into the gas phase, may have briefly driven some high-temperature chemistry, and may have allowed us to create a population of PAHs that we see today. So I'll just take a couple minutes here at the end and say, what else can we learn from these about the top-down versus the bottom-up routes? Well, bottom-up chemistry tends to follow a very particular trend in terms of abundances. So this is the cyanopolyine family, HC3N, 5N, 7N, 9N, and 11N, as measured in TMC-1. And you can see that they drop off about log linearly with abundance. HC11N is a little lower than otherwise expected. But this makes sense. As things get more complex in chemical families, you have less of them. Fine. Our PAHs, though, don't drop off in abundance with size. There's no fall off all the way up to cyanochlorine here, which is kind of wild, right? They're relatively consistent as you get larger and larger and larger. So how can that actually happen? Well, if you're building them from the bottom up, you would expect them to decrease. What would it look like if you're building them from the top down? Well, I'm going to tell you, I would naively expect it to go the other direction, right? Because if you imagine starting with a grandpa, which is not my pun, blame Xander Thielens, and breaking that down, well, there's a few different things you could break it down into, and each one of those breaks down into a few other things, and those breaks down into a few other things, and you end up with very, very small distributions, right? Start with a lot, and you end up with a little as you get smaller and smaller. Now, of course, some of these may be preferential. You may end up with preferred paths down here, but the trend should still sort of hold the same, right? The larger ones should be more abundant. You should be breaking them down into smaller and smaller things. So if you imagine adding 2 lines that go in opposite directions, they sort of come out to a flat line, which would be kind of interesting. So we need more information to work out what that eventually is, though. We need to fill in our gaps in the understandings of what PAHs are there. So these are all PAHs, these 2 in particular, that were detected in that asteroid that we have not yet found in TMC-1. Most of these do not have dipole moments, so we are adding CN groups to them. This one was known in the literature. These blue ones here, we are all synthesizing or have synthesized in-house. I have a very enthusiastic graduate student that does very scary wet chemistry in my lab to make all of these And we're now measuring and looking for all of these in our data. Now, most of them, unfortunately, have their strongest transitions here in KU band, where our observations are the noisiest. And the TAC for 4 years in a row has said we cannot have more time there. So we'll try again. We'll see if we can actually see any of these. The other thing that I sort of glossed over is this molecule here, fluoranthene. We haven't been doing too much of a look into it, even though it's there in TMC-1, because the QUIJOTE team actually took a look at it. They synthesized the 3-cyano derivative. This one actually has a dipole moment on its own as well, and looked for it in their observations, and they don't find it, which is interesting, although the upper limit that they place for it is right in line with all of our other CN-PAHs. So it could be that the observations just aren't sensitive enough to detect it. And maybe we add up all of the isomers or something, maybe we'll get a detection there, but see what's ongoing from there. And I'll just conclude by saying that we are actually a laboratory group. So I have a whole bunch of talented graduate students and postdocs that are just measuring nonstop new molecules in the lab for us to look at in space to try to fill in these gaps, both in the single ring and the multi-ring species. None of these we've actually detected in space yet, but as of a few months ago, we're up to measuring more than 350 molecules, which I think is pretty cool. The other thing that I think is really cool now, and when we think about PAH formation, is that we're now able to, I think, pretty directly connect 3 different stages of where these can be formed. In these evolved stars, where things are made very hot, in these cold clouds, where things are made very cold, and in the solar system, where our isotopic evidence says both are present. All right, so now the question is, which ones are made where, why, and what the relative balance of them are, and what that tells us about the observations that we're seeing in all of these other regions where all we have access to is the infrared and haven't yet had any detections in the radio. 3 minutes over. There's all the people that actually did all of this work. I'm happy to take questions for the next 27 minutes. Thanks.
Great. Thanks very much, Brett.
So somebody at Virginia, maybe Martian there or Ryan can help me
Moderate questions. So
Ryan itself has a question.
yeah, go ahead there with questions in Virginia then.
Great. Yeah, thanks for the overview. So quick question about your models that can reproduce those abundances or reproduce or not reproduce. Could a top-down chemical model reproduce the abundances or no? Even if you don't think it's kind of happening in that region.
So the question is, we have no idea because no such model exists.
Okay.
And the reason for that is twofold. One, even for the simple reactions from the bottom up, the vast majority of those are not measured in the laboratory. A good chunk of them are not calculated, and a good chunk of them that are in the databases have never been verified by anybody. So it takes a huge amount of effort just to fill those in. We haven't actually pushed our models past naphthalene, and we have detections all the way up to corny. Adding just reactions for proposal radical was an entire project for Alex on its own. Right. Same thing for the cyanobenzene. So then when you think about going from the top down, well, you have to choose what you're going to start with, and then breaking it down, there's infinite diversity and infinite combinations, right? And so that would be the most complex model ever generated by far. I wouldn't be surprised if in the next few years there were machine learned approaches to this that could actually do something reasonable. There are actually at MIT, there's a guy in the chemical engineering department by the name of Bill Green. His group, long before ChatGPT was a thing, used machine learning to generate reaction networks, kinetic reaction networks, just like we use in astrochemistry, for hydrocarbons and PAHs, and does it automatically and does it robustly. Generate thousands of molecules and hundreds of thousands of reactions, it's no problem. But the trick is that they have no knowledge of thermochemistry, meaning that they can't say whether or not there's reaction barriers for any of these. That's the challenge that machine learning has not been able to tackle. So his networks work exceptionally well for combustion environments where it doesn't matter, right? And that's why he built them, because he cares about combustion chemistry, because he's a terrestrial chemist, right? We just can't apply that technology yet to the interstellar work, but that's what we would want to do for the top down.
Yeah, thanks.
So Brett, let me ask then, just in the data, you said there are 4 components, kinematic components in TMC-1. So do they all have the same relative abundance of PAHs?
No. We have not it's on our list of things to do. We have not found a graduate student to sacrifice to it yet, to actually work out what the changes in those relative abundances are with respect to one another across the four components. The trick is that for the larger species, there are lower signal to noise detections. And so the error bars on the relative abundances between the four components for the PAHs are relatively large. For the small molecules, they're pretty well constrained. But we just haven't had time, honestly, to go through and do that analysis yet. It's on our list. But I can tell you just by eyeballing it, they are different. The relative abundances are different between the four components.
Right. Because that, I mean, I guess in all of these models, top down or bottom up, you'd be looking for variations. I'm just trying, this business of shocking the. So you imagine that you get rid of all the ice mantles with these shocks. Surely that would have an effect on the other just the normal chemical models you run for the cloud.
It would. So I said that this was plausible. There are actually some problems with the idea of it actually being shock chemistry. And one of the things is that what we don't see in TMC-1 is an abundance of oxygen-bearing species. There's almost no oxygen-bearing molecules in the gas phase. And that's because oxygen-bearing species at 10 Kelvin are frozen out on dust grains. And so if the shock model is actually correct, then what would have had to have happened is that shock came through, liberated a lot of things, the PAHs, the hydrocarbons, and the oxygen-bearing species. And then for whatever reason, in the time since that happened, only the oxygen-bearing species have preferentially frozen out and the PAHs have stayed in the gas phase. Differential freeze-out is a thing. I don't know that I believe that it could make the variation, the stark variation that we currently see. So I think that there's evidence that there were shocks. I don't know that there's evidence that those shocks evaporated the mantles completely. Yeah.
Mm-hmm. I mean, wouldn't you expect the PAHs to freeze out pretty quickly?
Very quickly, yes.
Yeah.
Time scale of 10. It'll start freezing out immediately. I think complete freeze out happens on a time scale of 1 million years or so. And TMC-1's a few 100,000 years old, right? So complete freeze out isn't expected, but they do freeze out starting immediately. They crash right back out. Yeah.
Mm-hmm. Well, then the dense regions would be different than the less dense regions, I guess.
Correct. Yes.
Great. Any other questions there in the Virginia side or online? Please raise hands.
Ryan has another.
I have another question.
Sure.
I have many questions, but I'll see how many I can get. Could you explain how you measure or how you detect the PHs when there's no rotational line? Do you look for CN transitions? Is that what you meant, or?
No. So if it's a pure PAH, say choranine, there's no signal whatsoever.
Yeah.
But choranine CN has its own unique rotational spectrum. And so that's what we're actually detecting. We are not detecting choranine. We're detecting choranine CN.
So it's like those two molecules are.
It's literally bound together. It's one new molecule.
Okay.
Yeah. We can use some theoretical work and modeling to try to back out an approximation of how much choranine must be there, given how much choranine CN we see. But yeah, and it's a factor of 30 or 50 more. But those are the error bars on that are large. Lots of assumptions.
Okay. Thanks.
Yep.
Yeah. So coming back then, it's clear. I mean, PAHs are definitely made in these carbon-rich stars, so that process definitely happens, right?
Yep.
And then you're saying that in the FUV field, they get broken down again. It's mainly by FUV, is it? So is there some?
So there's chemical degradation as well that happens, but the primary loss mechanism in really intense UV environments is UV degradation. But reactions with ions will just start breaking off pieces of it as well in some cases. There's some work by Sandra Brunken at the Felix Advanced Light Source in Nijmegen showing reactive destruction like that as well. So you can get chemical and photo degradation.
So is that cosmic ray processing basically, or is it reactions with ions?
Indirect in that the ions are generated by cosmic rays, but yeah.
Mm-hmm. So then, I mean, you might expect, again, variation in the diffuse ISM PAH content, with galactic environment. And I guess that's seen in the SMC, right? There's a relative
Yes.
absence of pH. Can you comment more on the environmental effects there?
Not with any intelligence, no. I am not an infrared PAH observer. So I agree. I saw lots of talks actually. Just last week there was a PAH conference in Ontario. The extragalactic folks see substantial variations in pH abundance and distribution, because from the infrared you can get ideas of the classes of pHs that are there, right? Small, large, ionized, neutral, nitrogen, decorated, and not. You just can't figure out which ones. So you do see variations in the composition based on metallicity, based on density. So the environment is definitely processing them, but I couldn't tell you off the top of my head what the direct correlations are.
Mm-hmm.
So let's see.
And we have no detections of PAHs in the diffuse ISM using radio astronomy. We did look. So that paper that I put up with the sightline towards Cygnus OB212 from Hensley and Drain, I helped them write a GBT proposal, and we pointed the GBT at that diffuse cloud sightline where we know there are PAHs, and we didn't see anything. So there's clearly not enough of them to excite radio emission.
Was there an upper limit on that abundance or not really?
We could place one. I don't think it would be meaningful. Yeah.
Okay.
At least not with our our present observations. If we wanted it to be meaningful, we'd have to get detections in the radio of something else that is there to compare to. We're not like CCO, so I'm not sure. Suppose we could look for HCO plus. I'm not sure what that ratio would give us meaning.
Well, on that theme then, so obviously you showed a lot in TMC-1. You mentioned this diffuse sightline, but what's the prospects for doing, obviously not as deep in so many different regions, but to look at different star forming regions, or to look at different kinds of molecular clouds?
So we did, with the original set of papers, we also searched for benzonitrile in a variety of other dark clouds. And so that was Andrew Burkhart's work. And we found it in every dark cloud we looked in. So benzonitrile being a single benzene ring with a CN, that was much more easily detected than cyanonaphthalein, takes less time, but we think is a good indicator that aromatic chemistry is there. So it seems to be in all of the dark clouds that we've looked at. We also detected it in a source called MC-27, which has an embedded, very low luminosity object protostar, which is kind of cool. So it's surviving there. And just 2 or 3 days ago, we published the detection of phenylene, a 3-ring PAH, in that same source. So we know that's present there after a protostar has at least turned on. And the Spanish team has found indene, this 5- and 6-membered ring fused together in at least one source outside TMC-1 as well. The trick with going to actual star forming regions, or like protostars like IRAS 16293, is that the temperature kills us. So these are very large molecules. They have a lot of rotational transitions. Their rotational transitions are all at low frequency. And as soon as you get up to like 20 or 30 Kelvin, the partition function kills you, because you just populate too many energy levels, and no single transition is then going to be bright enough to actually see. So what you're working with then is lines that are spread out, that are weak, and are at low frequency, and in a small source. So you're beam diluted in a single dish telescope. The lines are really weak, and the prospects are just bad. So for warmer sources, more compact sources, we're going to have to wait for ALMA, WSU, or probably the NGVLA would be my guess.
Would you have to worry about filtering out of extended emission with
those
facilities?
Yeah.
Or are they kind of, or the NGVLA, are they going to work on that?
Well, so you're going to, if in a source like TMC-1, I think the NGVLA would be able to do something there. I mean, we can do something with the VLA already, but it's real rough.
Yeah.
I think the very compact core of the NGVLA, you might be able to do it, especially if you had GBT mapping observations or something to go with it.
Yeah.
The 40-meter telescope, the Spanish use, they already mapped TMC-1 with a single dish map. It's a single dish map. They're beam's huge, but it is a map, so you can get the extended sources like that. For the more compact ones, I think that wouldn't be a problem at all for all or the NGBLA. We have a compact enough configuration to not resolve out things on the 10 arcsecond scale or whatever we'd be dealing with there.
What about infrared dark clouds, where these are more massive clouds? Like they're cold enough, I think, less than 15 Kelvin, but they have larger line widths typically. So
we had a few on a follow-up study proposal with the GBT. We didn't see anything in them when we looked at them, but we haven't investigated them thoroughly yet. I think we only looked at 2 maybe. And this was 5 or 6 years ago, so I may be remembering that list incorrectly.
Well, maybe we can
follow up on that.
That would be great. Please do. The GBT TAC got tired of us asking to look for this in other sources, but they're also tired of us looking for it in TMC-1. So,
right. Well, maybe they'll rotate off. So, anyway, let's see. What are isotopes? Carbon-13, is it standard? Or again, AGB stars, don't they have funny carbon-13 ratios? Could you tell something from carbon?
Yeah, they do. So funnily enough, our work on that was just accepted yesterday. So the idea was, can we look for the 13C enrichment ratio of benzonitrile or cyanonaphthalene and use that to do the same thing they did with the reboot results, back out formation temperature? We are never going to be sensitive enough to do the same sort of analysis that the reboot folks did. They look at double substitutions and triple substitutions and a bunch of other things. We're also not sensitive to see any individual 13C substitution in TMC-1 unless it was a 13C to 12C ratio of 1, which we're not going to hit. But if we look for the aggregate emission of all 13C substituted positions in PAH, well, in cyanonaphthalene, that's 10 carbons there or something, right? So that actually bumps the signal up quite a bit. So we did a study to see what levels we would be sensitive to. And the answer is, if the ratio was 40 or less, more or less, we should be able to see something at a 5 sigma significance. The ratio in TMC-1 for everything else is about 65. That's the local interstellar value. So the idea was, if it was formed in an AGV envelope, and many of them are heavily carbon-13 enriched, so say it has a ratio of 15 or 20 to 1, right? We would be able to detect that. So we also measured the spectra of all of the 13C isotopologues, benzonitrile and cyanonaphthalene, just like 40 different molecules, and did the experiment, and we don't see either of them, which means that it doesn't mean that they weren't inherited from AGV stars. There are AGV stars that have ratios of 65 to 1. It does mean that they weren't inherited from an AGV star that was heavily enhanced, right? So we were able to put some marginal constraint on that, but not a huge one. The Spanish team, led by Amanda Stieber, also a graduate student here in chemistry from Brooks Pate, measured the spectra of the deuterated versions of benzonitrile and looked for that. And also came up with a non-detection and indicated, got evidence that that was in situ formation as well. So none of this is, I would say, compelling evidence, but there's a bunch of small pieces of evidence that at least these small PAHs are probably made, if not entirely in situ, at least in part in situ in the cloud bottom up.
That's interesting, right? So I guess eventually you'd want to do it in the bigger species are harder to make from bottom up, right? But
yeah, so we'd love to do it for pyrene or for cornene. For the naphthalenes, those our instruments in the lab are sensitive enough to measure a natural abundance. So just buy a sample off the internet, make it, and we don't have to enrich it in 13C, and we can still measure the spectra in the lab, which is fine. For pyrene and for cornene, that is not the case. Spectra are not bright enough, and our instruments are not sensitive enough to do that. We have to enrich it. And the synthesis of specifically targeted enrichments of 13C in each one of these positions is so novel and challenging that my synthetic chemistry colleagues at MIT said we'll have to write several NSF grants before they can even figure out how to start doing it. So we're going to we're going to try to do it, but that I think we're like 5 or 10 years off from being able to robustly synthesize enough of those to measure in the lab.
Great. Any other questions on Virginia side or online on
The
the
pH topic.
One general question. So AGV stars versus these cold clouds, where have the most complex pHs been in radios? Is it in the TMC-1?
TMC-1,
Okay.
yeah.
And it's just because it's too warm in the AGV stars, like you said? Okay.
I think that's the case,
Okay.
yeah.
Okay.
We did put in an ALMA proposal to try to look for benzonitrile in an AGV star, IRC plus 10 to 16. Rejected with prejudice. Sorry, Mark. We may try again.
Okay.
Could you do it with VLA or something like that instead?
Certainly couldn't do it with the VLA. WSU or NGVLA.
Okay.
Yeah.
Same thing.
Or I mean, according to Mark's calculations, and they're good calculations, I think we actually could do it with ALMA if it's there. It's just the text.
It's also worth noting that the Spanish team has so much data on IRC 10216, and they have definitely been looking for it deep within their spectra, which they haven't published any upper limits on it so far, but I imagine that if they had it in their very sub-millikelvin spectra, it would have been published by now. So that also makes proposing for it tricky.
Yeah. Okay.
Yeah, that's fair.
Sorry, just a follow-up question. You said too warm, but is it in the sense of like they're not efficiently formed or like they're destroyed?
In that the spectra are harder to see because the lines are weaker because the partition function is too large. Yes, I think the chemistry is fine. Yeah. Did I see a hand back there?
Yeah, I heard at some point that things like fullerenes have been detected in space. Are they formed like a similar regime to the rest of the pHs you talk about, or are they like their own pathway?
But if it's a great proposal for a professorship for you to start your own group. It's a huge active area of research. You could just by thinking in your head about picture sense, you could build these larger and larger PAHs and imagine that at some point they're just going to stop being flat and turn around and form a cage, right? Form C60 or C70, which we have seen in space. But those processes are still up substantially for debate if that is the pathway that happens or if they are formed from completely divergent pathways. The C60 on Earth was actually discovered because Harry Kroto couldn't figure out why those cyanopolyions I showed you, HC3N, 5N7, and 9N, existed in TMC-1. That's the whole motivation. But the way that he tried to make them was he just took a carbon rod and hit it with a laser. And they didn't make the cyanopolyions that made C60. And so making these carbon allotropes does not require going through PAHs first on Earth. There are certainly ways to do it, and some groups have shown that you can actually take these pH structures, make them larger, turn them into bowls, bring bowls together, but it's not clear that that actually happens in space. As well, the places where we have seen fullerenes, these TC-1, this protoplanetary nebula, as far as I understand, the PAH abundances there are weird. But the number of places with detections of C60 is relatively low compared to the number of places with pH detections.
Has anyone okay, so when you say that like on Earth or something like that during that initial experience when they discovered fullerenes or whatever, there was like a sample of what would you say, was it graphite or?
Yeah, just pure carbon.
Yeah, bombarded by a laser. So that would be like an instance of like top-down formation of pH in the broad sense, right? Or
I would actually consider that you start with the carbon and you form that C60 and then stop. So if it had first formed like C360 and that had broken down into C60 in the end, I would consider that top down. They're stupid names. This is why they're bad names, but it's what we're stuck with.
okay. But I have a question. So people would if you did have a top-down scenario, would you oh, I know, never mind. Would you expect it to be more or less fullerene than like in a bottom-up scenario? If you were because I know it's in a top-down scenario, would you expect it to because it's more fullerenes I guess are pretty stable. Once you get there, would they stop breaking down, would you think?
Yeah, for the most part, fullerenes are extremely stable. You can ionize them. That's how we have the only DIB carrier that's known as C60 plus. They do react. You can decorate them with a hydrogen or a CN group or some oxygens, but the whole cage structure stays in place the vast majority of the time. The interesting thing though is I don't believe that there's a huge amount of fullerene formation in evolved stars. It's primarily in these planetary nebulae that's been seen. I could be incorrect on that point. But I think that if we were going to say that the top-down PAHs probably wouldn't be coexisting with fullerenes then, right? So if you're inheriting these from an AGB star, I don't know that we would necessarily expect to see fullerenes in TMC-1, which we don't see, but I don't know that anybody's actually looked hard. So I don't know if that answers your question.
Oh yeah, it does.
Okay, great.
Do we see fullerenes in this asteroid return material, or do you know?
I don't know off the top of my head. I want to say yes, but like with a 1.5 sigma confidence.
Okay, because you're saying they're so stable, they should be preserved.
They should be, yeah, exactly.
Well, you mentioned these astrochemical networks trying to model these things, and perhaps you can comment. I mean, it seems so complicated, all these species, and I mean, even networks to do very relatively simple things are complicated enough. So what are the prospects here for really, having a good network?
Either we sacrifice graduate students to it, or we get machine learning that actually works. So adding naphthalene to the network was a pretty heroic effort by a combination of Chris Shingledecker, graduate student, UVA, and Andrew Burkhart when they were here for the original reactions. And as far as I know, nobody has attempted to push that any further. I had a graduate student that added a few additional contextual reactions around those, but we've made no attempts to push it forward to pyrene, or certainly up to coronene. That's a grad student thesis without machine learning. I think is the answer. There could certainly be other groups around the world that are going to do this before we do. Loizon and Ugo Iacovella and Valentin Wakelam are thinking a lot about this. So hopefully they do it, which would be great because then we wouldn't have to.
Mm-hmm.
So with the machine learning, would you have to worry about the same thing you talked about with that other group at MIT validating, like the barriers and other aspects?
Yep.
It would create them, but someone have to go through and check.
Exactly.
Okay.
Which is why I think at the moment it's not an efficient way to do it. And in fact, I think it would introduce more uncertainty than it would help solve. So if somebody can find a way to do it and to also reliably infer reaction barriers or not, then maybe. Okay. Right. But the key is it has to only spit out reactions that we know go at low temperature, or spit out all the reactions and assign them an activation barrier. Right. Which I don't know if that could be possible. Machine learning changes every 6 months or something, right? But as of right now, nobody has managed to do that. I see the question back there.
Yeah, I just did a quick one. So from above, like when you add bottom up reactions to the network or something like that, do you know if they mainly gas phase sort of reactions contribute, or are they happening on dust grains and then they just desorb or something like that later?
So essentially 100% of the chemistry that we add for PAHs to the network is gas phase chemistry. The network contains grain surface reactions as well, but the only grain surface interaction with PAHs that we've added so far is losing them to the grain surface. Primarily because we don't know how to get them back off the grain surface, and because the chemistry to actually react them on the grain surface is much more complicated than in the gas phase. So it is a known failing of the models that they almost exclusively focus on gas phase chemistry at the moment.
Well, we're at the top of the hour here, so let's stop now. There's many other things we could discuss, but let's thank Brett for a great talk and discussion.